Okay, welcome back to linear algebra. We're going to finish up section 2.4, where we've been talking about invertible linear transformations, talking about something called vector space isomorphisms. Okay, so I want to define what I mean by isomorphic vector spaces, then I want to characterize them. Characterize isomorphic vector spaces, that's theorem 2.19. I want to show you that the vector space of linear maps from V to W is isomorphic to the vector space of matrices of appropriate dimension. That's theorem 220. And then I'm going to leave the proof to you, but theorem 221 is about something called the standard representation of V given an ordered basis. Okay, so that's our outline. Let's start by recalling in the case where you have two vector spaces with the same dimension, then there's a lot of ways to check on the invertibility of a map from V to W. Yeah. So in particular, you need only check its one-to-one. You don't have to check its onto. If the dimension of V and W are the same, the rank nullity theorem in particular implies if T is one-to-one, then it's onto, so it's invertible. Or vice versa. If it's onto, it has to be one-to-one. So that's kind of very special to linear maps, that you only need kind of half the usual ingredients. Okay. Likewise, those are kind of conditions that being onto, well, that's equivalent to its rank being as big as possible. The rank is the dimension of V. Or the dimension of the null space is 0. That's also equivalent. Like we saw last time, if the matrix in any ordered bases, beta and gamma for V and W respectively, if the matrix of T in that ordered basis pair is invertible, then the map is invertible. So there's lots of ways to check to see if a linear function between two vector spaces of the same dimension is invertible. Yeah, and in fact, if V and W don't have the same dimension, then we saw last time that no linear map from V to W could be invertible. It might be one-to-one, or it might be onto, but it can't be both if the dimensions aren't the same. Nice. So here's the main definition. We're going to say that two vector spaces are isomorphic. V and W are isomorphic, well, if there's a linear map between them that's invertible. Okay, and we'll call such a map an isomorphism. So really, isomorphism is just a synonym for invertible linear map. All right, and for some symbols, we're going to sort of write this V squiggly equals W when V is isomorphic to W. All right, so just to emphasize that if this linear map is given, it's an isomorphism if and only if, well, it has to be linear and it has to be invertible. Okay, so an isomorphism kind of has two components. It's a invertible linear map. And when we have one, we call the vector spaces isomorphic. The first main theorem is theorem 2.19. Let's check it out. We have two vector spaces V and W. They're finite dimensional. Okay, then one of them is isomorphic to the other. V is isomorphic to W if and only if they have the same dimensions. So this is what I was calling in the opening. I didn't write it here. Maybe I can write it. This is a characterization of isomorphic vector spaces. Why am I calling it a characterization? Because it's an if and only if theorem that says when two vector spaces are isomorphic. And it's kind of amazing that the only thing you need to be true for the vector spaces to be isomorphic is for their dimensions to be the same. Any two vector spaces of the same dimension are isomorphic. There's an invertible linear transformation between them. Okay, so how to prove this? Let's suppose that we've got our vector spaces V and W and they're finite dimensional. That's kind of my lazy way of writing that. So the dimension of V and the dimension of W is not infinite. And let's suppose that they're isomorphic. Okay, so by our brand new definition, what does that mean? That means that there's an invertible linear map from V to W. Right? So by our work last time, it was what we called the lemma. That means the dimension of V is equal to the dimension of W. So really, the half of this theorem is just sort of repeating that lemma. If you're isomorphic, then there's an invertible linear map, and that means the dimensions have to be the same in the finite dimensional case. So the first half of this theorem is really just that lemma that we proved last time. So what about the other way? If you give me a vector space V and its dimension is n, which is the same as some vector space W, how do I write down this invertible linear map? Well, again, all the machinery we need has already been developed. Let's let beta and gamma be bases for U and V, usual notation, ordered basis. And then I'm kind of reaching back, not too far, but in Theorem 2.6, back when we talked about linear transformations for the first time, given an ordered basis and then a subset of the codomain, there's a unique linear map, T. You can specify the value of T on the basis vectors. And here I'm going to say, well, T of Vj is Wj, right? So there's one and only one linear map that sends the jth basis vector in V to the jth basis vector in W. And I claim that linear map is one-to-one and onto. And since V and W have the same dimension, it's part of my hypothesis here in this theorem, I don't really need to show that it's one-to-one and onto. I can just do one of them. So I'm just going to do onto. So for an onto proof, if you give me a vector W in the codomain, I'm just going to write it as a linear combination of the gamma basis, right? So I know there's unique scalars AI that's true. So then I just defined V to be the same linear combination, same scalars, but take it of the VIs. So in particular, V belongs to my domain vector space. And then by linearity, T of V pushes through and gives me W. Right? Stop the video and look at those equations, but I'm just using the linearity of T. That shows T is onto. V and W have the same dimension, so it has to be one-to-one, so T is invertible. So T is an isomorphism. So V and W are isomorphic by definition. Cool. So any two vector spaces of the same dimension are isomorphic. So in particular, if the dimension of V is n, then V is isomorphic to just the column vectors Fn. So I was kind of alluding to stuff like this before, where I was saying there really isn't very many different vector spaces. Once you know the dimension of a vector space, up to isomorphism, quote unquote, there's just one, right? So just to give you some examples, I would know that, say, polynomials of degree less than or equal to n is isomorphic to the n tuples, or n plus one tuples, because those vector spaces both have dimension n plus one. And in explicit isomorphism, you could take a polynomial, its coefficients are called a0 through an, and just associate it to this n plus one tuple. We've talked about that before. Or likewise, the matrix vector space, its dimension is m times n. So it's isomorphic to just fmn. Yeah, you can just think of the matrices, the rows of the matrix. I'm just going to kind of do this schematically with the laser pointer. Just take the rows of your matrix and organize them into a big long vector. It would have m times n components, and that'll be a vector space isomorphism. Okay, Theorem 220 is the next one that I wanted to talk about. The good news is we've already proved it. What does Theorem 220 say? If you give me two vector spaces, right, and then usual notation, finite dimensional with bases beta and gamma, ordered bases, then the function phi, that's the Greek letter phi, that takes a linear map from V to W and associates its matrix in those ordered bases, I claim that's a vector space isomorphism. Yeah. So one consequence of this, not one consequence, but another way to write this symbolically, is that the vector space of linear transformations from V to W is isomorphic as a vector space to the vector space of matrices. This is good news, because if you're like me, you sort of understand matrices a little bit better than you understand linear transformations. So Theorem 220 is saying that anything you want to know about a linear transformation, you can answer in terms of a matrix. All right, so we've already proved this, actually. I'm just going to kind of let you do some digging through the book. I hope as you watch these videos, you'll stop this a lot, look these results up, and so on. But that Theorem 2.8, when we talked about linear transformations, showed that this map phi is linear, right? Remember what phi does. Phi of a transformation is just the matrix in these bases, beta and gamma. So the fact that we have this equality, the matrix that goes with the sum of T1 and T2. Here I didn't quantify, so pardon me. So for all T1 and T2, maybe I wrote this. Yeah, I did. I wrote it at the end. Sorry, I get a little mixed up in my video production here. My video production skills are not that great. But for any two linear operators or linear transformations in any scalar, Theorem 2.28 said that these two equations hold. And that's exactly the statement that phi is linear. Yeah, because if we kind of write in what this is, the left-hand side of this I'm trying to rush too much. On the left-hand side of that equation, that is phi of T1 plus T2. And this side is phi of T1 plus phi of T2. That's exactly the additive part of linearity. This one is the scalar multiplicative part. Okay, I'm going to send you back to the video where we proved theorem 2.8, because right after I got done proving it, I remarked that this map, I didn't call it phi there, but it was one-to-one and onto. We showed that it was bijective. So it's a one-to-one onto linear transformation. It's an isomorphism. That's all the theorem said. Cool. So as a corollary of that, if V and W have dimension n and m, then we know now that the dimension of the linear transformation vector space from V to W is m times n, because that's the dimension of the matrix algebra, the matrix vector space. Nice. All right. So now I got a little bit of a blank slate here. I wanted to draw as I talk to you guys to introduce this thing that we're going to call the standard representation of V. So let me kind of draw what people in this business call a commutative diagram. So say we have some vector space V and another one W, finite dimensional, and then say we have some linear transformation T between them. I can go like that, get a nice arrow there for T. So T is a linear transformation between V and W, all right? And say we have some bases, say beta is a set of vectors V1 to Vn. It's a basis for V. It's a subset of V I'm writing. Gamma, usual notation, W1 up to Wm. It's a basis, ordered basis for W. Okay, so if I pick a V in my vector space V, then I have already defined what we mean by the coordinates of V with respect to the beta basis, right? Where does such a coordinate vector live? It lives in the vector space Fn. And so I'm going to think of a map, actually. If I think of the map, it didn't go as well as I wanted it to. I was supposed to make a fancy arrow. There we go. I'm going to call this map phi sub beta. And phi sub beta of V is just the coordinates of V in the vector space beta. Okay. And of course, we can do that for W as well. We've got W over here. We've got a basis for it called gamma. So that's going to take a vector in W and give me an M vector, right? A column vector with M coordinates in it. So if I write over here the image of V under T, that's an element of W. Well, that vector T of V has coordinates in the gamma basis, and that would be a column vector with M coordinates in it. Yeah. And then we also know that there's a map between Fn and Fm that's given by the left multiplication by the matrix, and I'm going to just write the matrix notation. It's T in the bases beta and gamma. And we've proved before that if you take that matrix, T, in the ordered bases beta and gamma, and left multiply with it the coordinates of the vector beta in the vector V in the beta basis, you exactly get the coordinates of the vector T of V in the gamma basis. So I just kind of want to say what I mean by that in this diagram. I mean, if you start up here in V, there's sort of two ways to arrive at a vector down here in Fm. One way is you can take T of V to get a vector in W, and then take phi sub gamma of it to look at its coordinates. So that's this expression. Or you could first look at the coordinates of V in Fn, and then left multiply by the matrix of T in these bases. That's this expression. And the fact that they're equal is usually denoted in a diagram like this by putting a little circle. So that circle means that the diagram is so-called commutative. And it's just a visual way of sort of understanding the equation that's written at the bottom and highlighted in yellow. All right. Cool. So this is sort of a sophisticated way of saying that I can sort of swap my linear transformation between two vector spaces for matrices and column vectors once I choose the ordered bases. Once you pick beta and gamma, you can convert this thing into questions about matrices and coordinate vectors, right? Good. So this has a name. Maybe to keep my diagram visible, I'll scroll out just a little bit here. I hope that doesn't make it too small. But this is a definition of, if you like, in the section, this map, phi sub beta. It's called the standard representation of V with respect to beta. So why the word representation? Well, because once we choose the vectors of the basis beta, this phi sub beta gives us a way of understanding vectors in V as coordinate vectors. So we're representing them as coordinate vectors in Fn. So that's why it's called the standard representation. And I'm going to leave it as an exercise to you. I'm not going to prove this here in this video. I'm going to end the video. You're going to prove Theorem 2.21 that the standard representation of V in respect to beta is an isomorphism. It's an isomorphism. So I'm going to scroll back up to what I think is my beautiful diagram. I showed you that we kind of write isomorphisms with these wiggle squiggles. So sometimes people will just write, oops, wrong pen. You write that same squiggle next to the arrow. Either side of it, I'm going to write it on the right. That's kind of a way of showing that this thing is an isomorphism. All right. So this squiggly arrow means isomorphism. So V and Fn are the same. V is dimension n, Fn is dimension n. They're isomorphic by our previous result. Phi sub b is a very standard, or a very, very specific isomorphism. It's called the standard representation. All right, so I hope that was useful. I'm in class. I hope we'll do some more examples, but thanks for listening.